Welcome to The Explainer. Today, we are diving deep into one of the most intuitive yet surprisingly powerful algorithms in all of machine learning, the decision tree. Here's what we've got on tap. We're going to start with the absolute basics of what a decision tree is. Then, we'll get into the nitty-gritty of how it actually learns from data. We'll build one step by step, see how it handles tricky data, learn how to keep it under control, and finally, we'll give you the final verdict on when and where you should use one.
All right, let's get right into it. At its core, a decision tree is something you already understand, even if you don't know it yet.
So, the whole idea behind a decision tree is to answer this one big question. How can we get a machine to figure out a set of rules all by itself, just by looking at examples, instead of us having to code every single if this then that statement by hand? Think about it like this simple flowchart for deciding whether to go to the beach. You start at the top. First question, is there work to do? The answer is no, so we follow that branch. That leads to the next question. What's the outlook? It's sunny, so we follow that branch to our final decision. Go to the beach. See? Each question is a node. The possible answers are branches, and the final outcomes at the end are called leaves. It's really just a series of simple questions that are super easy to follow.
So what makes these things so useful in machine learning? Well, for one, they require almost no data prep. You know how with some models like K-nearest neighbors, you have to scale all your features so that age and income are on the same playing field? You don't have to worry about that here. They can also handle numbers and categories right out of the box. But the real kicker is that they create explicit, human-readable rules, and that makes them the perfect building block for even more powerful techniques like random forests.
Okay, but that leads us to the million-dollar question. How does the tree actually learn which questions to ask, and what's the best order to ask them in to build the most effective flowchart?
Well, the algorithm is what we call greedy. It starts with all your data mixed together in one big pile. At every single step, its one and only goal is to ask the single best question that will split that pile into the most homogeneous groups possible. It's all about creating pure nodes. You know, imagine sorting a mixed bag of apples, bananas, and cherries. A great first question would be, is the fruit red? That one question perfectly separates the apples and cherries into one group and the bananas into another. That's the whole game, the pursuit of purity. So, to put a number on this idea of purity, we use a metric called the Gini index. Now, don't get too hung up on the formula you see on the screen. The intuition is pretty simple. Imagine you have a bucket with 5 red balls and 5 blue balls. If you reach in, grab one, and have to guess its color, you've got a 50-50 shot of being wrong. That's maximum impurity, which corresponds to a Gini score of 0.5. But if the bucket has 10 red balls and 0 blue ones, your chance of being wrong is 0. That's perfect purity, a Gini score of 0. The algorithm's entire job is to find the questions that get those Gini scores as close to 0 as possible.
Another popular way to measure this is with entropy. This idea comes from information theory, and it's basically a measure of disorder or randomness. A dataset that's a 50-50 mix is super unpredictable. That's maximum entropy. A dataset where everything is the same is perfectly predictable. That's zero entropy. So when a tree uses entropy, its goal is to make a split that results in the biggest information gain, which is really just a fancy way of saying the biggest drop in randomness.
So, Gini or entropy? Which one should you actually use? Well, in the real world, the differences can be pretty subtle. But as you can see here, Gini is computationally faster because its formula is simpler. It doesn't have that logarithm. And that's exactly why it's the default choice in major libraries like scikit-learn and used by the famous CART algorithm. Entropy, which is used by older algorithms like ID3 and C4.5, is a little bit slower, but some people find it works slightly better on imbalanced datasets. Honestly, for most projects, Gini is your go-to.
All right, enough theory. Let's get our hands dirty and see how this works with a real, classic dataset to make it all click.
Here's the classic play golf dataset. Our mission is simple. Predict whether we should play or not based on the weather. The decision tree needs to figure out which of these features, outlook, temperature, humidity, or windy, is the absolute best first question to ask to get the purest split.
And this is where the magic happens. The algorithm goes through and tests every single feature. Let's just look at outlook. If the outlook is sunny, the data is still pretty mixed, giving us a Gini of 0.48. Same for rainy, but look at overcast. Every single time the outlook was overcast, the decision was yes. 4 yeses and 0 no. That's a perfectly pure node with a Gini score of 0. That one split is incredibly powerful.
The algorithm does this math for all the other features too, and it finds that splitting on outlook gives the biggest bang for its buck, the biggest drop in impurity. So that becomes the very first question, the root of our tree.
Now, this process of splitting doesn't just go on forever. A branch stops growing when it hits one of these conditions. It might be because the node is already 100% pure, or maybe you've just run out of features to ask questions about. And as we'll see in a bit, we can also set our own rules, like telling the tree not to grow past a certain depth, or not to bother splitting a node if there are too few data points in it.
Okay, so far we've been using nice, clean categories like sunny or rainy. But what about raw numbers? You know, things like temperature or income or a person's height.
The way it handles numbers is actually pretty clever, if a little brute force. Here's what it does. First, it takes all the unique values for a feature, say temperature, and sorts them from smallest to largest. Then it calculates the halfway point between each adjacent pair. Each of these midpoints becomes a potential question, like, is the temperature less than or equal to 71.5 degrees? Then the algorithm just goes through and tests every single one of those potential split points, calculates the Gini score for each one, and picks the split that gives the purest result.
And you can see that process right here with this taxable income example. The algorithm tests all the possible split points. It sees that splitting at 110,000 gives a Gini score of 0.343. Not bad. But then it finds that splitting at 97.5 thousand gives an even lower Gini of 0.300. That's our winner. The tree locks in that rule for that node. Is taxable income less than or equal to 97.5K? And now we've arrived at maybe the most important concept to understand about decision trees. Their greatest strength, that amazing flexibility to create super specific rules, is also their greatest weakness. It leads to a huge problem called overfitting. So here's the danger. If you just let a decision tree grow wild, it will keep splitting and splitting until it's created a rule for every single data point. It will perfectly memorize your training data, including all the random noise and flukes. This is overfitting. The tree will look like a genius on the data it's already seen, but it will be absolutely useless on new data. To stop this, we use these control levers called hyperparameters. We can set a max depth to stop it from getting too deep. We can set min sample split to tell it, hey, don't even bother splitting a group if it's this small. And min samples leaf makes sure that every final decision is based on a reasonable group of examples, not just one or two weird outliers.
This whole process of controlling the tree's size is called pruning. The most common way to do it is called pre-pruning, or early stopping, which is exactly what we just talked about, using those hyperparameters to stop the tree from growing too big in the first place. There is another method called post-pruning, where you let the tree grow all the way out, and then you trim back the branches that don't add much predictive power. But in practice, pre-pruning is usually faster, simpler, and gets the job done.
So, after all that, let's pull it all together. What's the final verdict? When should you actually reach for a decision tree in your machine learning toolkit?
Well, the verdict is pretty clear. A decision tree's absolute superpower is its interpretability. It's what we call a white box model. You can literally print out the rules and show them to your boss and they'll get it. That is incredibly valuable. But its kryptonite is overfitting. If you don't actively control it, it will almost always overfit your data. They can also be a little unstable, meaning even small changes in your training data can sometimes lead to a completely different tree structure. And putting it side by side with other algorithms really drives the point home. Look at that interpretability row. It's rated high, way above models like KNN or Naive Bayes. It also makes zero assumptions about your data, unlike Naive Bayes, which has that big feature independence assumption. But that freedom comes at a price, and you can see it right there in the overfitting risk row, high. This table perfectly captures the trade-off. With the decision tree, you get incredible transparency, but you have to be the one to manage its complexity.
And that brings us to the end of our explainer. A single decision tree is powerful and transparent, but we've seen its weaknesses, that instability and tendency to overfit. This leads to a really fascinating question. If one tree is good, but flawed, could we fix those flaws by using an entire forest of them? That's a question for next time.